Hi, welcome to Rebound's Lab. So today what we're going to talk about is freeze point suppression. Freeze point suppression can be a little bit confusing because it's a spontaneous process. What that means is that it happens on its own. So when people normally think of the freezing point of ice, they think of 0°C or 32 Fahrenheit. And what we're going to do is we're going to actually introduce a chemical that's going to lower that freezing point. So inside our environment, which is going to be one of these flasks, what we're going to do is we're going to lower the freezing point of the ice, and we'll see the ice spontaneously adjust to that new freezing point. What's happening on a molecular level is you can think about it kind of like a party. The ice molecules inside the chunk of ice are pretty content to just hang out in the ice until we introduce that freeze point suppressant. And then that freeze point suppressant makes the party really interesting, and the ice molecules just really want to go and mingle with that freeze point suppressant, and so they leave the ice. So you can think about it like the freeze point suppressant is actually motivating the ice to melt. It's not melting the ice, it's not attacking the ice is melting on its own because it wants to. And the reason why that's happening is that the freeze point suppressant is introducing a bunch of disorder into the system, and that causes the ice to want to melt at a new, lower temperature. So what we'll see is we're going to put some ice in the beaker, we're going to mix the freeze point suppressant with it, and we'll see the temperature adjust to that new freezing point. And how that'll manifest itself is a lower overall temperature. We'll also observe that the ice melts a lot more when we mix that freeze point suppressant. And again, that's because the ice is melting on its own spontaneously. So let's start. We're turning on our temperature sensor. Looks like it's working well. And we're just going to start by mixing up just some plain old ice with no freeze point suppressant. And this is just going to be our control, and it's also going to let us see how much more ice melts when we mix in that freeze point suppressant. So here we're just mixing it up with the thermocouple, and what we should see here is the temperature should be approaching 0, just the melting point of ice. So yeah, we're down to about 0.6, and we keep going and get down to exactly 0, but it would take quite a while. So let's just cut it there. So there we have it, just plain old ice. You can see not a whole lot of it is melted. Okay, now let's move on to the more interesting examples. So we got some more ice. So we're going to start out with just some Morton table salt. This is something that you could do at home, or impress your friends. Knowledge of freeze point suppression. So here we're just going to mix plenty of salt and ice. Mix it together, and this is kind of a tricky mixing process because they're two solids. But right away, we'll start to see some melting. So what's happening here again is the salt, the presence of the salt is causing the ice to adjust to a new melting point. And, everything is just driven by the order of the system. And the salt just introduces a bunch of disorder that the ice just motivates the ice to really get out there and mix with the salt. So we'll start to see here the temperature is probably coming down. Okay, so we're at about -14, -15. So you can see we're well below the freezing point of ice. And again, that's all because of the presence of the salt. Now what's interesting is you can see we've melted quite a bit of the ice. And that melting, again, is spontaneous melting caused by the presence of the salt. Okay, so let's move on to the material that we use in our system. Salt is a great freeze point suppressant, but what we found with a lot of testing is that the salt works great on the melting side, but on the separation side, it's really tough to remove salt at such a high concentration from water. So we moved on to use volatile materials. So here I'm going to use some methanol, which is what we're using in the system right now. And again, I'm just going to mix a little bit with the ice. And you might think that methanol is, pretty different than salt. It's a very different chemical composition. It's a liquid at room temperature, not a solid. But what we're going to see is the exact same process happening. And this is because the molecule and the composition of the molecule is not really what's driving the freeze point suppression. Instead, it's its ability to mix with the water. And so There are chemicals that the ice find much more interesting to mingle with, but really it has to do with how much, or how well the chemical and the water mix. And so methanol works just as good as salt because they both really like to mingle with water. So let's see what temperature we're getting down to. Yeah, -11. So again, we're getting well below the freezing point of the ice, and that's just because the presence of the methanol is causing that new equilibrium, just instituting a new regime of where the ice wants to be, and the ice is melting to adjust to that new equilibrium. So -13, we'll just call it there. So here you can see two examples of freeze point suppression. And what's really interesting to look at is just how much ice actually melted. Let's just go through the temperatures one more time. So here we have the ice right around 0, as you'd expect. We have the salt water, again, well below 0. And then we have the methanol, also well below 0. So I hope this helps you understand a little bit about freeze point suppression, and I hope you enjoyed the video. Thanks for watching.